How is a Bayesian graph a Markov chain? So this is a model of the world. How is that a Markov chain? Yeah, each node has its own set of states. Yeah, so the number of states of the whole thing is actually the product of the number of states of each node. So this alone is, if all these are binary nodes, it's 1, 2, 3, 4. It's 2 to the 13th power possible states for this Markov chain, even if it's a binary node.
And if you're in continuous space,
then it's obviously infinity.
Multiple infinities.
Yeah, it's infinity to the nth power. Okay, so this is a big Markov chain, 2 to the 13th power, even if these are binary nodes. And from each one of those states, there's some probability of transitioning to all of the other possible states. And most of them are 0, because there's a lot of transitions that won't happen, but some of them have probabilities. And I guess the closed form way to compute it all would be to do the same thing we did with that other Markov chain, which is consider the probabilities of going to all possible states, where states are the combinations of all values. And if you follow that through to the end, it would converge. And when it does, you could eventually know the likelihood of all the values, because even how they're affected by the likelihood of all the other values. And the thing is that would be nasty, but in theory it could be done by a Turing machine. And the cool insight of Gibbs sampling is this: even though there's a lot of nodes that are all affected by each other, if you pretend all the others are fixed and resample just one node at a time, it still works. The whole thing still stabilizes and converges to the same stable distribution that it would have converged to if you treated the whole thing as a great big Markov chain. So there's the intuition behind it. And now how do you code up Gibbs sampling? And basically at the intuitive level, I've already described it. Hold everything else fixed, resample a node. Pick a new random one, repeat. There you go, there's Gibbs sampling. But remember, we do have to consider the probability of it given everything that affects it. Remember that? Okay, so let us now ask the question, what affects the probability of a node? I'm going to copy this to Paint so we can play with it. And so for right now, we're going to assume we're going to resample this orange node and pretend the values of everything else are fixed. Okay, so all the other nodes have now taken on their values. And pretend we also know the probability distribution of this node given those two nodes. In fact, we know the probability distribution assigned to every node in this graph given its parents. That's what we know. And now I want to ask you, which nodes do we need to consider to resample this node? Yeah, so we have to consider its parents' nodes. I'm going to claim that we can nix this node. I was hoping to flood fill that. Apparently I've got JPEG artifacts in here. All right, then I'll boost my tolerance. Haha, okay. Black means you're out. I don't have to consider that one because remember I have a fixed value on its parent node. And we said fixed values make a wall for that chain of arrows, right? And that also implies I don't need to consider the value of this node, because knowing the value of this node means I don't care what your distribution is, I'm only affected by the value of that node. Okay. What about this node? Can it affect the value of the orange node? I think it's clear the answer is no. Well, it's actually kind of not that clear, but you're right, it doesn't. Let's just say no for now, because this one blocks that chain. So this one cannot affect this one, and there's no other path to the orange node, so we know we're good. Same with this bottom node. That one's black. Why? Because knowing the value of its parent leaves it with no path to affect the orange node. Yeah. Yeah, everything in this whole graph is observed, including even the orange one, but we're going to say, hey, we're not sure that observed value is good anymore, so we want to resample it. But everything hasn't observed, I guess, let me say it's temporarily observed. We've actually observed nothing, but we're pretending we've observed it by drawing from the distributions of every node. And we're going to let it go until it converges, and then we're going to finally open our eyes and look at the real world, and the values should at least follow the same distribution as the real world. Yes. It's parents and its children. Let me put it this way. If you remember the IQ graph that we did, if you have a good job, does that say anything about your IQ? Well, anecdotally, no. But just probabilistically, yes. Because if of all the people who have great jobs, there's probably a higher mean of IQs than the people that don't. Because IQ does affect getting a job. Okay? So again, I have to remind you, there's a difference between an anecdote and a distribution. Okay? So yes, we have to know this thing. And finally, these two nodes over here, we do have to know because remember the last lecture explaining away? Let me go over that really fast again. This is, orange node is you are intelligent. Green node is you are super lucky. Blue node is you got a great job. Okay? If we know you got a great job, then knowing that you're a darn lucky person, by the way, I don't even believe luck is a thing, but let's say we do. Pretend we believe luck is a thing, or maybe it's parents' wealth, I don't know what it is. If there's some other reason to explain how you got the job, what does that say about how intelligent you are? You see how they inversely affect each other. So that's explaining away. Intuitively, we'd kind of like to say we can get rid of these nodes too, but it turns out you can't. If you get rid of those nodes, you compute the wrong answer. You have to take into account all of your parents, all of your children, and the parents of all of your children nodes. And if you do that, then you're doing the right thing in Gibbs sampling. Okay. This is what's known as the Markov blanket. Markov blanket. And this is kind of the grand insight that ultimately made Gibbs sampling work. It basically says it's okay to put blinders on and just resample one node at a time as long as you compute its new distribution given everything in its Markov blanket. And it's perfectly fine to ignore everything not in its Markov blanket. And if you do that, then Gibbs sampling works. Then the graph converges to the true joint distribution. Then you can predict all kinds of crazy values about the universe, and it's fun and interesting and like that. Okay, so Markov blanket is really the grand secret behind MCMC. This right here is the key. The key insight is you have to know your parents and your children and the parents of your children. Okay, and now Markov chain Monte Carlo. You know, just to make sure we've got something to attach to that acronym. Do you know what Monte Carlo sampling is?
Yes.
Okay, well, I'm going to explain it anyway. What is the area of this blob?
Throw darts at it.
We're going to throw darts at it. Okay, you guys really do get Monte Carlo sampling. Well, I'm going to throw so darn many darts at it that my darts are green, by the way. It looks like that because I took all of the dark green darts and I threw them out. And I know the area of the whole square, and basically I can subtract all the ones that landed inside the thing, and I can count the number of darts and find the ratio between the number of darts and the area of the square, which is the row times the height. And now I know the area of the thing, and that's Monte Carlo sampling. Okay, so MCMC stands for Markov chain Monte Carlo. Markov chain Monte Carlo. I think Monte Carlo is a city where gambling is allowed, and the idea of Monte Carlo in computation implies this whole idea of using random chance and then using that to compute something definitive. I believe that the world's most accurate clock in the world are the atomic time clocks, which they have on the geosynchronous orbiting satellites that compute geoposition. And the way they work is they count the number of times that I think an alpha radiation particle is emitted from some radioactive substance, which emits them randomly. And you might say, wait, the world's most accurate clock is based on randomness? And the answer is yeah. If we just count how often these things that are coming out completely randomly are emitted, well, we know the distribution with a lot of high precision and accuracy, and counting that produces the most accurate time estimate of anything that we know how to estimate. Because given enough randomness, it just turns out to be darn predictable. And so Markov chain Monte Carlo is a predictable way to get good results, even though it's based on randomness. What we're doing is randomly picking new values for these things. So that's the Gibbs sampling component. And yet it's going to converge to the true distributions. So that's the deterministic Monte Carlo component of it. And the fact that the whole thing is a Markov chain, which will eventually converge to a stable distribution, is the other part of it. And so basically these words mean do Gibbs sampling until the thing converges, and then you know the joint distribution. First we'll look at it in math form, and then I'll go through the pseudocode form. Of course, this is the one you really want to know because you're going to just copy and paste that in your code and turn it into Java or C. But we're trying to learn. I want you to understand the math first too. No, this is the stable distribution, meaning so that means that assume every node does follow the distributions you have assigned to it. Given that assumption, let everything go wild for a darn long time. What are the distributions of the values they're going to spit out after a long time? That's the stable distribution. So it is really the distribution of a system that has reached homeostasis or balance.
Well, I
or
guess it depends if you're